contribution is on the p-type region and the N+ region not so much. Okay, it can be 100:1 essentially. Okay. So the next question is what is hot carrier effect and propose 3 methods to solve blah blah. The hot carrier effect is part of lecture 3. So essentially what happens is when we make our source and drain very close to each other, that means we are making very small devices and you're still applying a high drain voltage, there is a very high electric field. That high electric field can accelerate this carrier. So a hot carrier is essentially a carrier with a lot of energy. Okay. So when the carrier is going and hitting the interfaces, it can generate more electron hole pairs. And for example, in this case, a hot electron is going, hitting, generating more holes. That holes go into the substrate. So one consequence is the substrate current, which is not so problematic because we can collect the substrate current, we can apply a bias, etc. to control it. The bigger problem is the damage of the oxide surface. Okay, because we cannot do anything if this oxide layer is damaged. That means essentially the electrons are like bullets. It comes, hits, creates electronic defects, not surface roughness, electronic defects. Okay, and that electronic defects can trap carriers. Okay, so in the picture in the lecture note, there shows how your transfer characteristic changes when you have damage, when you don't have damage, etc. Okay, when you have damage, you need to apply more voltage to fill up all the cracks and form the channel. Okay. So in the lecture, for sure, you have been introduced to one way of reducing the hot electron effect, which is that
LDD.
LDD is the process way of doing it. Okay. So the other way is to go towards different conditions where the operating voltage is lesser. So standard is to go to 5 volt, the conventional, but then now we have circuitry with 3.3 volts, 2.5 volts, etc. So, but again you can see it does not make a dramatic difference. You are still in the same order of magnitude, right? Let's say your transistors go down 10 times, 20 times, by the voltage just it goes down half of it. It's not so huge difference, but people still do that because the probability of hot carrier formation goes down. Okay, so that's one way. The second thing is something called duty cycle, which is you don't turn on the device so often. So you make more devices such that not one, instead of one device doing the work, you have 5 devices doing the work. So each device needs to be turned on only 1/5 of the time. So in certain critical areas, etc., you do not let the device run at high voltage, such that the probability of this recombination reduces. Probability of the damage reduces. So what it means you have to maybe make more complex circuitry or you have to make more transistors to share the circuit. Okay? So that's another trick that you could try. The third trick is what we know about the lightly doped drain. Okay?
Yes.
So in yesterday's lecture, we talked about how we make the lightly doped drain, etc. Lightly doped drain essentially means we are building a N- or a lower doping concentration interface at the source and the drain location. Okay? So that N- location will essentially have high resistance, and although you are applying a plus 5 volt, not all the 5 volt falls across the channel. Okay? Some of it falls across this resistance, some of it falls across this resistance. So we are artificially eating away the voltage. It's not that great because we are heating up and things like that and more complex process flow. Right? That was the first trick that was done. The final thing people do is to try and make your gate oxide more robust. Okay? So as I told you, one major problem is this gate oxide getting attacked. So what people, for example, have done was when they were using silicon oxide, they would add nitrogen into the silicon oxide. So it becomes silicon oxynitride. Because silicon oxynitride has more robustness towards this damage. So even if there is a damage, maybe the defects it forms is not so shallow that it traps a lot of carriers. So you change the material essentially to make sure that the trapping is not super high. So this is the fourth way you can do this thing. We only talked about, so the bottom two are what as process based people we can do. The other two are more related to the electrical engineering approaches to try and mitigate the dynamics of hot carrier effect. Silicon oxide network.
Yeah, as in like it's the same function in a sense to block off further damage.
Okay. So this is some information I needed to
So
know.
like silicon oxide still works.
Okay.
Silicon oxide.
Technically, tutorial time is done.
It's just that that's copying.
Thank you for your attention. I'm still here if you want to ask me questions, clarify anything. I want to make sure if somebody is outside, they can come and look at more tutorial. Yeah.
This is how you mentioned that's how you get rid of that substrate current, right? You can increase the bias.
So, in some of the devices, actually, you have something called a base contact. So the base contact, you can just will draw it so that especially it does not allow the electrons to go there. In certain cases, you actually have something called SOI. The whole thing is